We are, Hi, we're going to see Introduction to Sequence in this lecture. And this is one of the cornerstones of natural language processing at the moment because there are a lot of language tasks that deal with translating sequences to sequences. So, what do I mean by that? Both input and output are sequences of text. So, in this case, it means that we can see it in machine translation, summarization, dialogue generation, chatbots. The applications are endless. And the beauty of sequence to sequence architecture is that you can use any sequence and pair it with any sequence. So that means I can even take a video, which is a sequence of images as input, and generate subtitles, which is a sequence of text. So it's a sort of mixed media format where all you need is the sequential information. It does not matter where it comes from. So these are the components of a sequence to sequence. It has an encoder decoder architecture and it has a series of RNNs. For example, if it's a sentence to sentence, then each RNN would take in the cell would take in the embedding of the word and then concatenate it together. And each sometimes you can even do each of the words as an RNN with characters and then go on. It's very interesting because in translation, we don't use RNNs for words, but we use RNN at the character level because it brings about much better translation. So we need to choose at what gradation we are going to use that RNNs and then use the corresponding embedding. So I'd like to start with a couple of terms. First is padding, where the sequences are padded to a fixed length. We saw this in recurrent neural networks as well. So even though we are identifying the varying input length of the sequences, in practice it is after all a fixed length vector and the remaining are filled with another symbol and this symbol in our embedding will have a corresponding vectorial representation. Then we need to identify the starting and the end of a sequence so that you can use anything. These are some of the commonly used ones. There are even BEG, END, and so on. Then there is unknown, which we saw sometimes we limit the vocabulary size, so we would have unknown, or it never occurred in our um, word embedding dataset. So that's also an important token. So in our embedding, we need to have these tokens represented as well. So to get started, we have an RNN for encoding the input sequence into some internal representation. And this is passed on to the decoder, which is trained to predict the target sequence. There are a lot of issues here. First of all, it's a complex model because you have a lot of RNN and a lot of internal weights. And technically, we would be using LSTM or GRU, as we saw in the previous lecture, which handles the exploding and vanishing gradient problem. And this is done in a joint manner. Because it's trained in a joint manner, we get the essence of sequence. We see what it is in the input sequence that is truly modeling the output sequence. If I train the encoder and decoder separately, all I would have is a language model for the input and the output. So the fact that these are connected and trained together is what makes sequence to sequence work. So this is the diagrammatic representation. When I have my input, I pass it into an RNN and I have the hidden states flowing through and representing the sequence. And this is passed onto an encoder vector. Now, if you remember, LSTMs also have outputs. So here we would actually have outputs, but we discard them. We don't care what the outputs are, and we pass on the encoder information, which is basically a function of the input and the hidden state. So this is the part of the encoder. Similarly, in the decoder, we don't care about the inputs. We pass on the hidden state and generate the outputs. So this is a very naive architecture of sequence. However, why waste that information of output and input? Sometimes what we do is we model the language anyway and pass on, if this is x1, we pass on x2, x3, and so on. So these output values are not used for evaluation, they are discarded at the end. But while training, we still use the output values with some language models. Similarly, here also, y1 would have a y0, which is like any symbol we saw last slide, and y2 would have y1. So this is something I'm saying as an example. You can have any other outputs here or inputs here to make the model perform better. So how do we train this? Training is backpropagation throughout, and we know that the RNN separately will have backpropagation through time. And as I said, this is one of the features we do to improve our performances. Where time shifted by 1 simply means if I have y1, y2 here I will have y0, y1. So this we saw throughout actually in RNNs and other language modeling tasks. So this you can imagine it is much better than passing y1, y2 again here. You're not learning much about the language if you simply pass the same sentence as input and output. But when you make it a sort of predictive task, you again enforce the sequence information, and the information coming from the encoder vector is also passed in. So what this does is the encoder vector becomes your H0, your hidden state 0, and that is passed on to the remaining RNN. So to summarize, the input sequence is passed to the encoder and the encoder outputs are discarded. Now the hidden states are forwarded to the decoder and then learning proceeds. Training is pretty straightforward because you have both the encoder input and the decoder input. For example, if I'm translating, I have pairs of sentences from the input and the output. So I have pairs of sentences in, say, English and then Tamil. So I have two parallel corpus which are stating how it's going to be translated. But what about inference? The problem with inference is, okay, I only have an input statement of one language. So I had said we have variants where we can pass in inputs here and have outputs here as well. So if I have inputs here, I cannot pass that during inference time because I don't know what the value is going to be. Of course, the nice way is to like forget that these things have outputs, these things have inputs and train the network. But there's a very interesting way of getting around this and still evaluating the sequence model. What we do is, so once I send this in, now I know that the starting of the sentence is this token, go. So initially what I do is I give this sentence and I pass it in, I get the encoder vector. And then what I send into the model is basically go and then pad and things like that. So once I do that, I will predict the first word. Then what I will do in the next iteration, I will send go the first word that was predicted and then pad the vector. Then go first word predicted, second word predicted, and then the rest of the network. Are you guys clear with this, what I said?
Yes. Yes.
Yes,
Okay.
ma'am.
Cool. So this is called feature forcing, where you are forcing at inference time to predict the output in a particular way. So this I felt was very interesting because you are using the structure of language to generate your inference time data. Whereas usually we would just have pairs of information that you can easily get at inference time. So this is called greedy decoding, where you basically say, okay, I've sent the start and then I get the highest probability he. Okay, this is a very funny sentence, which is it's saying he hit me with a pie end. So this is argmax, where you take the highest probability of the sentence and you keep forcing it and finally get the inference time. Can you think of any problem with this? What could be the potential pitfalls of using the maximum probability at every step? In general, what is the problem with greedy algorithms? You might have studied algorithms in your courses. So, whenever you have a greedy method, what
They get
disadvantage we face?
they get stuck at local minimum or local maximum.
I'm so sorry, I have not been here. Yeah, have you been able to hear me?
Yes, ma'am. I'm
Okay,
saying they get stuck at local minimum,
yeah, sort of.
local optimum.
Yeah, so that's sort of the idea where it's not. Yeah, correct. It's a local optima, and you can get stuck. You can't move further, and you might make mistakes. There's no way to go back once you make a mistake. So that's the problem with greedy decoding. Yeah, right? Uh, who said the answer? I was looking at the slides. Oh, Ayush. Okay. Um, so anyway, yeah. So we have the greedy decoding method, and this has this disadvantage that it's all well and good if really we were having the highest um, probabilities. But what if, like he said, we make a mistake or we are stuck at some point? There is no way to go back. So, to address this greedy decoding problem, we have what is called a beam decoding. So, to motivate it further, so if you have he hit me with a pie, so the first word translates to he hit and then goes to a. Now there's no going back because once I see the next word, I know that I have made a mistake while I translated. So, how do I fix this problem? So, this is where the idea of beam decoding comes. So, what this means is on each step of the decoder, I keep track of the k most probable partial translations. So, this is the beam size. In AI, we use beam search a lot, where we keep a set of hypotheses in a beam. Now, I'm sure you would have studied breadth first search and depth first search, and you would have seen that in both the searches, um, the space keeps increasing exponentially. You can witness it more in breadth first search, where at the first level, say you have one node, then you have two nodes, and then it will become four, eight, and so on. It exponentially increases. Why I'm referring to that is, in some sense, this is a search space, and we are selecting the top one at every level. If I were to do a breadth first search over the entire set of possibilities, I would have an exploding tree where all possible words would be there, and I would try and compute the multiplicative probabilities across the tree. But this is inhibitive, it's exhaustive, though it is guaranteed to find the optimum, especially in an algorithm like breadth first search. It might even be impossible on a computer in today's standards. So, what beam search does is it doesn't go through all the possibilities, but at every level we keep a set of beam. So this, I don't know if you have studied beam search in your algorithms course, but what this does is that
Yes, ma'am. Yes,
you have searched, you have learned that. Okay. So
yes,
what,
ma'am.
so you would have an idea that it takes the best of both breadth first search and depth first search, and has a bit of space, and it records that. And we will be using this in our sequence model. So we have two possible. So if here the beam size is 2, and we keep the top 2 at all times, and then we have the final um, search tree, and we take the highest probability across the search tree. So this is what we know as greedy decoding. Sorry, this is beam decoding. I should change the title. This is beam decoding, not greedy decoding. So in beam decoding, we saw the advantages, and to sum up, in greedy decoding, we decode until the model produces end. I forgot to mention that in greedy decoding, I was concentrating more on start, but we also stop decoding until we reach end. In beam search decoding, we produce different hypotheses. So if you see before, here there is an end here. Here both sentence, and then here end would have come much earlier. So once you get end, you don't stop. You just stop that branch of the tree. But here end comes to a bigger extent, or a longer sequence as such. So we don't stop when we reach end. We explore the search space in the beam manner. So when a hypothesis produces end, that particular hypothesis is complete. So that particular part of tree is done. But we continue searching our hypothesis. So where do we stop? When all your hypotheses have produced end, or you have reached a particular set of layers and you know that you're not going to be able to compute anymore, or you can't afford to, or you have at least n completed hypothesis, where n is a predefined cutoff, because you at least need one thing to come to n, right? So then you have, say, 2-3 sentences, and then you can decide which one to decode. So you can imagine this beam search decoding has a much higher guarantee of finding a better translation. So now there is one more problem. So I told you in the beginning that we have this encoder and we pass on the inputs, and then we throw away the entire network and pass it to this one single vector, which is the encoder vector that's going to be a hidden state. Now you can imagine that this entire long sequence has been sort of compressed, calculated, and put in here. And it's very hard to decode from there. Like that's a kind of logical conclusion. So what do we do about this? So to address this bottleneck, which is basically I have an encoder, it's collected at the end, and it has to capture all the information about the source sentence. And sometimes the source sentence might be much smaller than the target sentence. So in these kind of situations, it's quite hard for the model to learn and understand these nuances. So the solution for this is attention. So there's a very famous paper called Attention is All You Need, where propose this idea that, for example, in machine translation, if I say a particular sentence and then its corresponding sentence in another language, sometimes the verbs, the pronouns don't matter. It's the um, common noun or something like that which defines what is going to be translated. So this is what we call as attention. We figure out which part of the input is important for providing the translation. So what we do is on each step of the decoder, we have a direct connection to the encoder to focus on the source sequence. So we have these connections to the decoder, which says, okay, pay attention to this part of the encoder input, instead of having a single vector that decides how it should be treated. So what we do is that the encoder RNN, before it produces the output, we have an attention layer where you calculate attention scores, and the decoder has access to these attention scores. And here, after training, this it will give a high score at this point, because these are basically like common words, and this is it's a special word, and this is going to be the pipe in the sentence. So this is where you need to pay attention. So once I have this, I will be able to figure out that it should be pipe. So after this attention, you will also have the same outputs from here. So this part you will have outputs. This graph basically says what is here at this attention layer. So now the decoders not only have the sequence information from the encoder set, they also have access to the attention scores. And once again, these attention scores are also learned by training. So not only is it trained for the entire model, for every input there is an attention score. That is intuitive, because for this particular sentence, this is what we need to pay attention. For another sentence, it might be the first word you would want to pay attention. So because this is an RNN, these attention scores are a function of both the input and the hidden state. So you have elements of the sequence as well. And it is a function of every input that is accessible to the decoder as well. Now this has a lot of advantages. First thing is, as I said before, it has a lot of information for the decoder to capture apart from the encoder vector. It also says, it's not just any information, it says which part of the source to concentrate on. So this is what solves the bottleneck problem. You can bypass this bottleneck and look directly at the source. Now, even though we may use LSTMs, we still have a lot of vanishing gradient problems in the long-term case, where things become smaller and smaller. Now, attention provides you a direct link to the far away RNNs, so you need not depend on the encoder vector. And this is the most important part. It provides interpretability. So I can see an attention vector and tell you, look at this word and concentrate on this word. I can look at the scores, I can get alignment. So this is a matrix between the translated sentence and the original sentence. And I know that this pair between entarte and pi is very important for translation. And this is because we never trained also an alignment system. We were trying to just generate this translated sentence. And we are now getting a word by word alignment. And actually, alignment is a separate NLP task on its own. And sequence with attention creates this interpretable alignment. And interpretability is costly, and it is one of the drawbacks of deep neural networks in general. And this is one way we are working towards higher interpretability. So now we come to a more general definition of attention. So it's given a set of vector values and a vector query. Attention is a technique to compute weighted sum of values dependent on the query. Till now, we have not seen weights that are dependent on the query. We have seen weights more as a static thing, where any model given the query, you will just multiply and get the final one. So it's sort of a selective summary, and the query determines what values to focus on. So attention is a way to obtain a fixed size representation of an arbitrary set of representations. So this is, of course, but implementation wise, it is going to be a sort of, it's going to be a parameter of a function, and it is the function we are going to learn. And once you apply this function, you will get this representation for the same. So we have some values and a query S, and we can compute the attention score. We can send it into softmax to get a, whenever you use softmax, you'll get a probability distribution. And then you get the final attention output, which is going to be the product of the softmax and the input. So this is also called like a context vector, and you can compute the scores in many ways. We won't be going into that, but basically just to say that the way attention is able to do something for every query is basically this sum it takes over the input and the softmax that we have calculated. So the parameters of the softmax is what we are learning while training so that we know where to pay attention. Now, we can do many things. We can do dot product, which is basically the hidden state and the input dot product. Um, yeah, you can skip the notation. This is just to give an intuition. You can multiply the weights and have attention. You can add attention across time steps and so on and so forth. But of course, additive attention means that it will change the dimension. In all the others, the dimension is sort of handled. So here D1, D2 is like input and output dimension. And we'll be seeing like for different things, we use different kind of attention. And once this E is calculated, we then do softmax and get the final attention score. So to summarize, we saw sequence architecture with encoder decoder, and we saw how versatile it is. We can use all sorts of sequences, mixed media sequences, and so on. We saw how teacher forcing was done through greedy and beam decoding, and we saw how attention works. Now, this idea of attention is what we're going to see in the next class in transformers, which has truly revolutionized NLP, and we'll be seeing why that happens. And also, that involves some concepts of convolutional neural network, which is why I took it last lecture. And thank you.